question at hand involves upgrading communications equipment in a facility with existing electrical infrastructure that is approximately 40 years old. While the sub-panels met code requirements at the time of installation and through 2005, the communications team now requires an equipment ground running all the way back to the main distribution panel. The existing installation uses rigid conduit between panels, continuously bonded to the enclosure or ground bus. Current code favors PVC conduit, raising questions about the suitability of the existing rigid conduit system as an equipment ground. The key question is whether the existing equipment ground, as it's currently configured, is sufficient for the facility. If so, the responsibility for any additional grounding requirements falls on the communications equipment contractor. Civil engineers are responsible for providing a basic electrical connection, while specialized equipment support is typically the user's responsibility. The central issue is whether the sub-panel circuit, with its equipment ground, needs replacement all the way back to the main distribution panel. To address this, we must first consider whether the existing equipment grounding method meets current requirements. The current method, utilizing rigid conduit bonded to the enclosure or ground bus, was compliant with the 1999 National Electrical Code, which was in effect during the initial installation. However, the current NEC 2020 mandates the use of an insulated equipment grounding conductor, or EG, separate from the conduit or raceway in all sub-panels. This brings us to the question of responsibility. The communications contractor bears the responsibility for ensuring their equipment meets the current code requirements for equipment grounding. The facility owner, in this case the civil engineers, is responsible for providing a code-compliant electrical connection to the sub-panel. However, they are generally not required to upgrade the entire circuit back to the main distribution panel solely to accommodate the new communications equipment. In conclusion, the existing equipment grounding method does not fully meet the current NEC 2020 requirements, particularly regarding the separate insulated equipment grounding conductor. While it may be sufficient for the existing equipment, the communications contractor is responsible for upgrading the equipment grounding as needed for their specific equipment. The facility owner is not obligated to replace the entire sub-panel circuit to the main distribution panel unless there are other safety concerns or code violations that necessitate it. Therefore, it is recommended that the communications contractor install an insulated equipment grounding conductor in the sub-panel to comply with the current code. Furthermore, the facility owner should verify that the sub-panel enclosure is properly bonded to the grounding system. If there are any doubts about the safety or integrity of the electrical system, it is crucial to consult a qualified electrician for a comprehensive evaluation. To further clarify the requirements and responsibilities, let's delve deeper into the relevant sections of the National Electrical Code and explore practical considerations for implementing the necessary upgrades. When assessing the existing grounding system, it's essential to verify the integrity of the rigid conduit connections. Ensure that all couplings, connectors, and fittings are properly tightened and free from corrosion. Any loose connections can significantly compromise the effectiveness of the conduit as an equipment grounding conductor. Additionally, inspect the bonding jumpers that connect the conduit to the enclosure and ground bus. These jumpers should be of adequate size and securely fastened to provide a low impedance path for fault current. According to NEC section 250.4, grounding electrode systems must be effectively grounded and bonded. This means that all metallic components of the electrical system, including conduits, enclosures, and equipment frames, must be interconnected to form a continuous grounding path. This path should lead back to the service equipment and ultimately to the grounding electrode system, which typically consists of ground rods, ground plates, or connection to a metallic water pipe. The size of the equipment grounding conductor is determined by NEC Table 250.122, which specifies the minimum size based on the rating of the overcurrent protective device in the circuit. For example, if the circuit is protected by a 20 amp breaker, the minimum size of the equipment grounding conductor is 12 American wire gauge copper or 10 American wire gauge aluminum. It is crucial to adhere to these minimum size requirements to ensure that the grounding conductor can safely carry the fault current back to the source, facilitating the rapid operation of a current protective device and minimizing the risk of electrical shock. When installing a supplemental insulated equipment grounding conductor, it should be run alongside the circuit conductors within the same raceway or cable. This ensures that the impedance of the grounding path is minimized, further enhancing the effectiveness of the grounding system. The equipment grounding conductor should be connected to the equipment grounding terminal in the sub-panel and to the grounding terminal or bus in the main distribution panel. It is important to use appropriate connectors and termination methods to ensure a secure and reliable connection. Furthermore, NEC Section 250.130 outlines the requirements for equipment grounding conductor connections. The grounding conductor must be connected to the equipment grounding terminal of the receptacle or equipment. For permanently connected equipment, the grounding conductor must be connected to a grounding lug or terminal that is specifically designed for that purpose. It is crucial to avoid using screws or other hardware that are not intended for grounding purposes, as these may not provide a reliable connection. In situations where the existing rigid conduit system is deemed inadequate or unreliable, it may be necessary to replace it with a new raceway system that incorporates a dedicated equipment grounding conductor. This is particularly important if the conduit is corroded, damaged, or improperly installed. PVC conduit is a common choice for new installations due to its resistance to corrosion and ease of installation. However, PVC conduit is non-conductive and therefore requires a separate equipment grounding conductor to be installed within the conduit. When using PVC conduit, it is essential to ensure that the equipment grounding conductor is properly sized and installed in accordance with NEC requirements. Another option is to use metallic conduit, such as electrical metallic tubing or intermediate metallic conduit, which can serve as both a raceway and an equipment grounding conductor. However, it is important to ensure that all connections are properly tightened and that the conduit is adequately bonded to the enclosure and ground bus. Regardless of the type of raceway system used, it is crucial to perform thorough testing and inspection to verify the effectiveness of the grounding system. This includes testing the continuity of the grounding path, measuring the impedance of the grounding conductor, and verifying that all connections are secure and reliable. It is also important to document the grounding system, including the size and type of grounding conductors, the location of grounding electrodes, and the results of testing and inspection. This documentation will be valuable for future maintenance and troubleshooting. In addition to the requirements of the National Electrical Code, it is also important to consider any local codes or regulations that may apply. Some jurisdictions may have additional requirements for equipment grounding, such as the use of specific types of grounding electrodes or the installation of ground fault protection equipment. It is essential to consult with the local authorities to ensure that the grounding system complies with all applicable codes and regulations. In the context of upgrading communications equipment, it is also important to consider the grounding requirements of the equipment itself. Some communications equipment may require a dedicated grounding conductor or a specific type of grounding connection. It is essential to consult the manufacturer's instructions to determine the specific grounding requirements of the equipment. Furthermore, it is important to ensure that the grounding system is compatible with the communications equipment. For example, if the communications equipment requires a low impedance grounding path, it may be necessary to upgrade the grounding conductor or install additional grounding electrodes. In summary, ensuring proper equipment grounding is critical for the safety and reliability of electrical systems. The existing equipment grounding method in the facility may not fully meet the current NEC 2020 requirements, particularly regarding the use of a separate insulated equipment grounding conductor. The communications contractor is responsible for upgrading the equipment grounding as needed for their equipment, while the facility owner is responsible for providing a code-compliant electrical connection to the sub-panel. It is important to perform thorough testing and inspection to verify the effectiveness of the grounding system and to consult with a qualified electrician if there are any concerns about the safety or integrity of the electrical system. Remember, electrical safety is paramount and proper grounding is a fundamental aspect of ensuring a safe and reliable electrical installation. In the case of upgrading communications equipment in an existing facility, a collaborative approach between the communications contractor, the facility owner, and a qualified electrician is essential to ensure that the grounding system meets all applicable codes and regulations and provides adequate protection for both personnel and equipment. This collaboration should involve a thorough assessment of the existing grounding system, a detailed review of the grounding requirements of the new communications equipment, and the development of a plan to upgrade the grounding system as needed. The plan should address all aspects of the grounding system, including the size and type of grounding conductors, the location of grounding electrodes, and the methods of bonding and connecting the various components of the grounding system. It is also important to consider the potential impact of the new communications equipment on the overall electrical system. For example, if the equipment draws a significant amount of current, it may be necessary to upgrade the service entrance or the distribution panel to accommodate the increased load. Similarly, if the equipment generates significant electrical noise, it may be necessary to install filters or other mitigation measures to prevent interference with other equipment. By taking a comprehensive approach to the electrical upgrade, it is possible to ensure that the facility is equipped to handle the new communications equipment safely and reliably. This will not only protect personnel and equipment from electrical hazards but also ensure that the communications equipment operates at its optimal performance level. Ultimately, investing in a well-designed and properly installed grounding system is a wise investment that will pay dividends in terms of safety, reliability, and performance. When evaluating the existing grounding system, consider the age and condition of the grounding electrodes. Grounding electrodes can corrode over time, which can reduce their effectiveness. It may be necessary to replace the grounding electrodes if they are severely corroded or damaged. The NEC specifies the types of grounding electrodes that are permitted, as well as the requirements for their installation. Common types of grounding electrodes include ground rods, ground plates, and metallic water pipes. Ground rods must be at least 8 feet long and must be driven into the ground so that at least 8 feet is in contact with the soil. Ground plates must have a surface area of at least 2 square feet and must be buried at least 30 inches below the surface of the ground. Metallic water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. It is important to ensure that the grounding electrodes are properly connected to the grounding system. The connection must be made with a listed connector that is suitable for the purpose. The connector must be securely fastened to the grounding electrode and to the grounding conductor. In addition to the grounding electrodes, it is also important to consider the grounding electrode conductor. The grounding electrode conductor connects the grounding electrode to the service equipment. The size of the grounding electrode conductor is determined by NEC Table 250.66, which specifies the minimum size based on the size of the service entrance conductors. It is important to ensure that the grounding electrode conductor is properly sized and installed in accordance with NEC requirements. The grounding electrode conductor must be run in a continuous length from the grounding electrode to the service equipment. It must be securely fastened to the building structure and protected from physical damage. If the grounding electrode conductor is run through a metallic raceway, the raceway must be bonded to the grounding electrode conductor at both ends. Another important aspect of equipment grounding is the bonding of non-current carrying metallic parts. Bonding is the process of connecting all non-current carrying metallic parts of the electrical system together to form a continuous grounding path. This includes metallic conduits, enclosures, equipment frames, and other metallic parts. The purpose of bonding is to ensure that all metallic parts are at the same electrical potential. This minimizes the risk of electrical shock if a fault occurs. The NEC specifies the requirements for bonding in Article 250. Bonding jumpers must be used to connect metallic parts together. Bonding jumpers must be of adequate size and must be securely fastened to the metallic parts. The size of the bonding jumpers is determined by NEC Table 250.102, which specifies the minimum size based on the size of the circuit conductors. It is important to ensure that all bonding jumpers are properly sized and installed in accordance with NEC requirements. In addition to the general requirements for equipment grounding, there are also specific requirements for certain types of equipment. For example, NEC Section 645.16 specifies the grounding requirements for information technology equipment. This section requires that all exposed non-current carrying metallic parts of information technology equipment be grounded. The grounding conductor must be run in the same raceway as the circuit conductors. Similarly, NEC Section 518.4 specifies the grounding requirements for places of assembly. This section requires that all exposed non-current carrying metallic parts of the electrical system be grounded. The grounding conductor must be run in the same raceway as the circuit conductors. These are just a few examples of the specific grounding requirements for certain types of equipment. It is important to consult the NEC to determine the specific grounding requirements for the equipment being installed. When upgrading the grounding system, it is also important to consider the potential for ground loops. Ground loops occur when there are multiple grounding paths between two pieces of equipment. This can cause unwanted current to flow through the grounding conductors, which can interfere with the operation of the equipment. To prevent ground loops, it is important to ensure that there is only one grounding path between two pieces of equipment. This can be accomplished by using a single-point grounding system. In a single-point grounding system, all grounding conductors are connected to a single grounding point. This prevents the formation of ground loops. In addition to the technical aspects of equipment grounding, it is also important to consider the administrative aspects. This includes developing a written grounding plan, training personnel on proper grounding procedures, and conducting regular inspections of the grounding system. A written grounding plan should outline the procedures for installing, testing, and maintaining the grounding system. The plan should also identify the personnel who are responsible for each task. Personnel should be trained on proper grounding procedures. This training should include information on the NEC requirements for equipment grounding, the hazards of improper grounding, and the procedures for inspecting and testing the grounding system. Regular inspections of the grounding system should be conducted to ensure that it is in good working order. The inspections should include a visual inspection of the grounding conductors, grounding electrodes, and bonding connections. The inspection should also include electrical testing of the grounding system to verify that it is functioning properly. By addressing both the technical and administrative aspects of equipment grounding, it is possible to ensure that the electrical system is safe and reliable. This will protect personnel from electrical hazards and prevent equipment damage. Finally, remember that electrical codes and regulations are constantly evolving. It is important to stay up to date on the latest requirements and to consult with a qualified electrician if you have any questions.